Also, I changed my title. It seems to be a pattern here. But here, an example, a visual example in TED style, not with a lot of text, but just showing you some outlines of where the AI has found some ridge and furrow. But then also where the National Mapping Program found some ridge and furrow. A various approach. We've been just using LiDAR here to find remaining earthworks. National Mapping Program has used a lot more data sources, including aerial imagery. And so you can see that the ridge and furrow here, which is there in the middle, doesn't really have any kind of earthwork still remaining on the ground, but the polygon is there. And the farmer there has been applying for various grants to get sustainable farming initiatives, but actually last year this new polygon arrived and their grants have been taken away. And obviously they're not happy about that. They're complaining to their local authority and getting in frustration with them. It's inconsistent. They don't even see any earthworks there. How can their plowing methods actually impact the archaeological record there? And that's what AI can help with. It's not just knowing where these data sets, where the polygons are. We're very polygon rich, but metadata poor in some ways. And AI can fill those gaps in England across the country. So taking you back to AI, I've shown you a few outlines, but how does it work? What goes into something that detects these archaeological sites? So we use Earth observation data like LiDAR, satellite imagery, but also other mapping sources like historic maps. Train the AI with known examples. So we would outline archaeological sites with a polygon around it, or objects on historic maps, the objects of interest, we outline them, and then internally the AI will learn why we've outlined them, what is the thing that we've seen that it should start mimicking. It should start to understand that roundhouses appear in all sorts of different ways when an animal's been burrowing into it. It appears differently depending on various types of erosion from plowing or otherwise. And it should understand what the experts have been doing over 50, 100 years and why they've been outlining things. That's what the AI does. And in the end of the day, it's been inferenced then over large areas, and it will come up with some assessment of how the probability comes up with. It says, oh, I'm about 97% sure this is a roundhouse. In this particular case, it's a roundhouse that wasn't known before, and it's a new discovery. So that's great, but it will also come back with objects that might not be correct. So you're coming up with a probability just like you would want a human to do in some ways, because maybe they would outline a cattle feeder as a roundhouse or something like that. So there's that feedback that you get from the AI on uncertainty and potential other objects that it might think are there. So then taking you to other objects, well, the same object, the ridge and furrows, because we've mapped them on a national scale. So this then leads into that policy a little bit more. The Forestry Commission has asked us to map these ridge and furrow nationally, and we found that about 3% of the country of England still has ridge and furrow remains on it of varying degrees of preservation. So we didn't just detect it and then stopped. We also, within each polygon, assessed how tall is this ridge and furrow still on the landscape? Could we potentially date it? So we made it the polygons metadata rich, and we assessed the width, the depth, the angle variations to see if we could find that reverse S shape within the lines that we were able to extract, and really and even like slope and altitude, all sorts of data that can be used for research. But then what the Forestry Commission has done with this information is understand and see like how well is that preservation of particularly medieval ridge and furrow, which seems to be the one that is more there's more want to kind of protect those. So if perhaps there's a threshold like 20 centimeters that is worth anything 20 centimeters and over is worth protecting and not planting trees on, then that could be a policy that can be consistently applied across the country. Obviously, we've also outlined with this work that actually where there is these hotspots of ridge and furrow differ a lot, and some local authorities might actually say ridge and furrow is really unique to us, so that 20 centimeter doesn't actually fit us at all. We want to focus in a different way, but at least what this data does is it gives you a baseline to work from. It gives you those outlines of where there is this ridge and furrow, and then it can be feeding into local plans or otherwise with some data to back up what's out there. And here we're looking at ponds, national pond loss specifically. So you can see various locations outlined here where the ponds are no longer there. If you look at some of the ponds that are just to the left, they remain, but the ponds on the right are lost. So another thing that we've digitized then, these ponds on historic maps on a national scale, found that about over 500,000 ponds have been lost since 1900. So that kind of knowledge then informs a lot of potential restoration projects. Where have we lost all these ponds? Can they be, how was the connection of these ponds in the past? And can that connectivity be brought back in some ways? Can we highlight areas where that might need to happen? And those pond locations are not just important for us for heritage value of historic ponds, they're also important for being seed banks. They're called ghost ponds. They still have seeds of 100 years ago when they were lost. And so reviving those brings back the environment of 100 years ago as well. And some species might have not been seen for 100 years. So it's not just about understanding the sorry, it's making noise. It's not just about us working as the heritage people on our own. We're working together with ecologists, and we've mapped not just then the ponds, but also the entire historic map from 1900. So we know exactly where there was this yellow patch, which is rough pasture, where there is the bright green patch at the top, which is a deciduous woodland, or a mixed woodland there in the middle, and then those wetlands from the old river courses that now are just wetlands still curving through the landscape. So by digitizing these entirely, we can help reconstruct and restore the historic environment where it's just been drained and optimized over the last 100 years towards one goal of farming or of development and making land productive in some way. And we can support that kind of thing. And also some findings, well, this next slide. So here, I wanted to just talk a little bit about that frustration gap, the HR officers that are stretched with thin, asking to look at some polygons and saying that indeed, actually that's not the slide. Okay, I'm just going to move on to my next slide. So what we then think about is, okay, so we've got all these various objects. We've got our ridge and furrow. We've got our ponds. We've got individual objects. But to do that for all the archaeological objects, all the things, it would just be a big undertaking. Whereas we think that actually what we need to do is also have something that is just a model that finds all the banks, ditches, pits, and mounds, so that you can come up with some sort of support system that already outlines what's the likelihood of archaeology here. So it's not about finding exactly specific object types. It's just highlighting you to those hotspots, perhaps, where there might be a deserted medieval village hidden in the landscape still today because of those earthworks. And we know that it's perhaps from some modern ordnance survey data that area is now being farmed. So we know that, okay, those objects might be related to that. So so it's about probability mapping then in that case. So it's that. And what we then can do is not just understand that there still are these these banks and ditches and pits and mounds. What we also want to do is understand how tall they are in the landscape, like I showed with the ridge and furrows. So you can do that for each individual earthwork and start using that same model, but then on all these other objects and understanding how tall they are. So here you can very clearly see that under the woodland there at the bottom right, you can see the digital surface model from the LiDAR, and above that, the digital terrain model. You can see that under the woodland, some of these objects have been better preserved. And when you then look at this from our detection of all these banks, then also we can assess how tall they still are. But then you also end up, of course, with areas where they've been plowed entirely. And that's where we can't just rely on LiDAR data. We need other data sources to help inform that. And that's where we then need to bring in the aerial imagery. So we've also made some initial case studies where we were looking at finding crop marking in these areas. And this is kind of what we came up with. Again, we're not specifically saying, okay, these are houses, these are something specific in terms of the object that we come back with. It is actually just outlining where are the crop marks, and are they likely of archaeological archaeological nature, and then putting them all together in a model that then says, okay, on this particular field, maybe a local authority, a historic environment record officer might get our data in from one end, doesn't have to immediately integrate it into their historic environment record, which they would obviously also not have the funds to kind of look through all of our lines and things that we come up with. Is actually just having it there so that when it's needed to kind of assess a new field for a grant application from a farmer, then actually, they would be able to use this information and then start assessing it with just the added data. So thank you very much, and I welcome any questions.